One of the very important properties of dilute solutions is colligative properties. Now, you may be knowing that colligative properties are those properties which depend only on the number of solute particles present and not on the identity or nature of the solute particles. So these the colligative properties depend only on the number of the solute particles present in the solution, or rather we can say it depends upon only the concentration of the solution. Now there are basically four types of colligative properties: lowering of vapor pressure, elevation of boiling point, depression of freezing point, and osmotic pressure. These four properties depend upon the number of solute particles or the concentration of the solution, and not on the type of solute or the nature of the solute particle. Now in this video I shall be discussing with you the first colligative property, or one of the colligative properties, that is lowering of vapor pressure. Lowering of vapor pressure, you know that we need to know, to understand lowering of vapor pressure, we need to know what vapor pressure is. Now in a liquid, you must be familiar with vapor pressure when we discuss about the term boiling point. Now we shall see a bit more briefly what vapor pressure is in this video also. Now when you take a liquid with, when you take a solvent in a container, you have got the solvent molecules or the liquid molecules in it. Now there are molecules on the surface. Now these surface molecules tend to escape outside, that is, they tend to escape from the liquid phase to the gaseous phase. So you can see here these molecules try to escape from the liquid phase to the gaseous phase. Now if the system is open or the container is open, what happens? These gaseous molecules will escape out of the system. They will escape out of the system to the surrounding. So there will be a loss of matter. Now if you take a closed container, these molecules which are in the gaseous phase will remain above the liquid phase. Now after some time, for every molecule of the liquid which goes into the gaseous phase, there will be one molecule which will come to the liquid phase. So that means the gaseous phase and the liquid phase reach an equilibrium. At this stage, the vapor phase or the molecules in the vapor phase will exert a pressure on the liquid phase, and that pressure is called the vapor pressure of that liquid. So every liquid has got its own characteristic vapor pressure. Alright, now the pressure exerted by the vapors above the liquid surface in equilibrium with the liquid at a given temperature is called vapor pressure. Alright, and remember, every liquid has got its own characteristic vapor pressure. Now we usually say that the vapor pressure of a liquid depends upon the nature of the liquid and also depends upon the temperature, and it is designated as P0 solvent, that is vapor pressure of pure solvent. Or usually when we talk about a solution, we consider solvent as A, representing solvent as A, and we put it as P0 A when we discuss about the derivations and all. Now if in a solution we are preparing a solution with a non-volatile solute in it, alright, now what is going to happen there? Now here on the left side, on the right side, you have a solution, a solvent alone, pure solvent alone. On the left side you have a beaker filled with solution, solvent and solute. The red balls indicate solute and the blue ones indicate solvent. Now on the surface, when you compare a number of particles, solvent particles on the surface for a solution and a pure solvent, we find that the number of solvent particles of the solvent in the solution is less on the surface when compared to the number of solvent particles in the pure solvent. Now because of this, the number of solvent particles which enter the gaseous phase in a solution will be less when compared to the number of solvent particles which enter the gaseous phase in the pure solvent. And thus what happens if the system is closed? What happens? The solvent molecules, since the number of solvent vapors above the solution is less when compared to the number of solvent molecules above the solvent, the pressure exerted by the solvent molecules on the solution is less when compared to the pressure exerted by the solvent vapors on pure solvent. Thus, we can say that the vapor pressure of the solution has been decreased when compared to that of pure solvent. So, P0 solvent will be greater than P solution, or the change in vapor pressure delta P is given as P0 minus P. So the vapor pressure of the solution will be equal to the vapor pressure due to the solvent only. That's why there is a decrease of vapor pressure of the solution. So you can put it as P is equal to P0 A into mole fraction of A, because it depends upon the mole fraction of the solvent. Now, where P is the vapor pressure of the solution, P0 A is the vapor pressure of the pure solvent, and chi A is the mole fraction of the solvent. Chi naught A is the mole fraction of the solvent. At a given temperature, the vapor pressure of a solution containing non-volatile solute is directly proportional to the mole fraction of the solvent. Okay, so the vapor pressure of the solution containing non-volatile solute is directly proportional to the mole fraction of the solvent. This is the Rawl's law. We have already discussed this earlier. Now, this Rawl's law is related to the relative lowering of vapor pressure. Remember, vapor pressure and relative lowering is different. Both are different terms. Alright. Now, we have the expression P equal to P0 A into chi A. Now, if there are two components A and B, A is the solvent and B the solute, then chi A will be equal to 1 minus chi B. Chi B is the mole fraction of solute. Chi A is mole fraction of solvent. So you can put chi A as 1 minus chi B, and the expression will become P equal to P0 A into 1 minus chi B. And you rearrange it, you get P by P0 A equal to 1 minus chi B. And 1 minus, again simplifying this, you get 1 minus P by P0 A equal to chi B. Again doing arithmetical treatment, you get P0 A minus P by P0 A equal to chi B. Now this term P0 A minus P by P0 A is the relative lowering of vapor pressure. Okay, P0 A. The P0 A minus P is nothing but the difference in the vapor pressure, the lowering of vapor pressure. That difference divided by the vapor pressure of this pure solvent gives us the relative lowering of vapor pressure. That is, to what extent when compared to P0 A or when compared to the vapor pressure of the solvent, how much has been lowered. That is relative lowering of vapor pressure. So remember, delta P and relative lowering of vapor pressure both are different. Alright. Now, for a dilute solution of a non-volatile solute, the relative lowering of vapor pressure is equal to the mole fraction of the solute in the solution. That is what this expression depicts, the last expression, the expression which we have arrived at. Okay, so the relative lowering depends upon the mole fraction of the solute, while the lowering of vapor pressure depends upon the mole fraction of solvent that we have seen earlier. Okay, relative lowering of vapor pressure depends upon the mole fraction of the solute in the solution. So this is Rawl's law of relative lowering of vapor pressure. For a dilute solution of a non-volatile solute, the relative lowering of vapor pressure is equal to the mole fraction of the solute in the solution. That is Rawl's law of relative lowering of vapor pressure. Now this expression, this relative lowering of vapor pressure, we can connect it to the number of moles or the molarity or the molecular weight of the solvent. Now we have this expression P0 A minus P divided by P0 A equal to chi B. Okay, since P0 A is constant, at constant temperature we can say that P0 A minus P is directly proportional to the mole fraction of the solute, and hence it is a colligative property. The lowering of vapor pressure is a colligative property. Alright, So Rawl's law of relative lowering of vapor pressure applies to very dilute solution of non-volatile solute, and the solute also must understand that the solute must not undergo dissociation or association. It means there must not be any change happening to the solute. It must not undergo dissociation or it must not undergo association. When we say dissociation, it is nothing but getting ionized or dissociated, and it must not undergo association indicates it must not form a dimer or a combination of molecules. Alright, now let us see how we are going to relate this to the molecular weight of solute. Now we have this expression for relative lowering of vapor pressure, which relates to the mole fraction of solute. Now this can be written as delta P by P naught T equal to chi V. Now we know that chi B is nothing but number of moles of B divided by the total number of moles of solute and solvent, NB by NB plus NA. Now since for very dilute solutions NB is less than NA, that means the number of solute will be less than the number of solvent, NB plus NA or can be put as NA. So chi B will be equal to NB by NA. Alright, now we know that chi B equal to, NB will be nothing but weight by molecular weight, and NA will be weight of A divided by molecular weight of A. Put that in this expression. So you get the relative lowering of vapor pressure equal to WB by MB divided by WA by MA. You rearrange it, you get this expression delta P by P naught A equal to WB MA by WA MB. So the molecular weight of the solute MB will be equal to WB MA P naught A divided by WA delta P. So you are relating the lowering of vapor pressure to the molecular weight of the solute. So if we know the lowering of vapor pressure, we know the molecular weight of solvent and weight of solute, we can calculate the molecular weight of solute. So this is how we apply this colligative property to determine the molecular weight of the solute dissolved in a given solution, to understand what is the solute present in the given solution. Okay, so using this expression, you can solve a lot of problems. You get a lot of numerical problems related to this. So try to solve problems related to the determination of molecular weight of solute using the lowering of vapor pressure. Alright, now in terms of molality, what you can put it as delta P by P naught A equal to molality into molecular weight of solvent divided by 1000, where M is molality. Okay, and that is given by WB into 1000 by WAMB. Well, how do you get this? This term, that is, you multiply and divide by 1000, you get this term. So you are converting the relation between the molecular weight or the relative lowering of vapor pressure to molality. Alright, so the relative lowering of vapor pressure can be expressed in terms of molality. It can be expressed in terms of molarity also. Hope it's been clear to you. If you have any clarifications, feel free to ask and try to solve numerical problems related to this. Thank you.